So the first example I'm going to do is not going to be terribly exciting, but let's say that this is the function y equals 1 plus 2x. And I wanted to find the area from 0 to 3. So the truth is that I could give this problem to somebody in pre-calculus. I could probably, if I put this on some graph paper, give this to a 5th or 6th grader to come up with the area. Because this is a shape that we actually know how to find the area of. This thing is a trapezoid. So if push came to shove, you could use geometry to figure out the area of this shape. You could either break this into like a rectangle with a triangle on top, or you could use the area equation for a trapezoid. I'm going to use the trapezoid area equation. So I need to know the two heights, because the area for a trapezoid is 1/2 times the base times the heights added together. I'm going to call that h1 plus h2. So if I were finding this using geometry, I'd come in here and say, okay, well, that first height, that's happening when x is 0. So if x is 0, y is 1. And that second height is happening when x is 3. And when x is 3, I'm going to get 1 plus 6. So I'll get a height of 7. And then the base here is 3. So if I were just thinking geometry formula, this area is 1/2 of the base times me adding the two heights together. So 7 plus 1, I'm going to get 8. So it looks like I've got 24 and then times 1/2. So that area is 12. So I just want to preserve this and say, we know that this actual area is 12. Okay. Now I'm going to switch gears a little bit. I'm going to ask a question that we're not really going to answer, but just to illustrate a point. So if this is that same function, y equals 1 plus 2x, and I were trying to find the area from 0 to 3, and for no reason at all, I said that I wanted to approximate this with n equal to 7. Actually, I'm going to give myself just a little bit more room at the bottom here. Now, I would never really choose n equals 7 if I could avoid it, because that is going to make for some ugly numbers. But I actually want to practice with the ugly numbers really quickly. So if n equals 7, then I know the width of each of my rectangles is going to be 3 minus 0, because it's the total width of the part that I'm trying to find the area of, divided by the number of rectangles. So the base for each of my rectangles is going to be 3/7. So now I'm going to come in here and start putting my rectangles in. So that first rectangle, because the width has to be 3/7, that first rectangle, the x value is at 3/7. And we didn't say whether we wanted to do left-hand endpoints or right-hand endpoints. Let's choose right. So my next rectangle coming in here also has to have a width of 3/7, which means that 3/7 plus another 3/7 would be 6/7, but I'm going to be lazy and just say that's 2 of my 3/7. That's my first rectangle, my second rectangle. So I'm going to get to my third rectangle here, and that's going to be 3 of my 3/7. And I would keep going, and since we have 7 rectangles, by the time I get to the last one, and I'm going to have to squeeze them in here, so 3, 4, 4, 5, 6, 7. By the time I get to this last rectangle, that's supposed to be 7 of the 3/7, which is good because those would cancel out and give me the 3 that I know is the x value at the end. These numbers are a little bit messy, but where I'm going with this is, sorry, now I got to erase this board again. Where I'm going with this is that we want to be able to have a nice way using summation notation to write down and add up all of those rectangles. So if I come back in here, and here's my y equals 2x plus 1, and I'm still going from 1 to 3. So if we did 7 rectangles, but we wanted a better estimate, we could do 40 rectangles. And if we wanted a better estimate than that, we could do 100 rectangles. But in order to actually exactly find the area under here, I would have to put in an infinite number of rectangles so that the width of each rectangle gets really, really small. So the way that I'm going to do that is I'm going to say that we have n rectangles. So I can't really draw n rectangles in there, especially if that's going to become infinite. So I'm just going to fake it and kind of get started. So we know that my delta x is going to look like 3 minus 0 divided by n, because that's how many rectangles there are, or 3 over n. So when I go to draw these in, here's my first rectangle. And since the width of that rectangle is 3 over n, that very first x value is 3 over n. Now I'm going to go to my second rectangle. And so that next x value that I'd be plugging in, I've moved over 2 of the 3 over n's. When I get to my third rectangle, I've moved 3 of the 3 over n's. Now, I know that we're trying to shove an infinite number of rectangles in there, but because I can't draw them all, I'm going to go ... and draw in my ith rectangle. Now, I is the indexing variable. It's an arbitrary choice. If you've been watching YouTube videos, sometimes folks use k instead of I, so just watch out for that. So on my ith rectangle, I will have moved over I of the 3 over n's. So this right here is like my generic x value that we're going to use to figure out the area of this generic rectangle. So I know that for my ith rectangle, the area is going to be the base times the height. And that base is the same for each of my rectangles. Each rectangle has a base of 3 over n. The height of my rectangle is going to come from taking that x value and plugging it into our function. This is where life gets a little bit messy. So when I plug this into my function, we'll have 2 times the x value plus 1. And our x value was I times 3 over n. Once we've written what the area of my ith rectangle looks like, that's when we can switch this over to summation notation. And I can say that if I want to add up all of the rectangles, then that area for adding up all of the rectangles would look like the sum of this, starting with my first rectangle. And because we said we were going to have n rectangles, my last rectangle is going to be my nth rectangle. So if we expand this out here and do a little bit of algebra with this, I am now looking at the sum from I equals 1 to n, and here I've got 3 over n, and then inside these parentheses, if I distribute that 2, then this looks like 2 times I times 3 over n, or 6I divided by n plus 1. And then I can multiply the 3 over n through. And I've got I equals 1 to n. 3 times 6 is 18. I over n squared plus 3 over n. Now this is the place where in Dr. Diddell's lecture on Wednesday, he gave us some formulas he gave summation formulas for adding up a constant, adding up an I. And so those summation formulas are definitely things that you're going to want to memorize. And the ones that he gave out in lecture on Wednesday, I did put into the Canvas page, and I'll pull those up just a second. I see that there are a couple of questions in the group chat, and so I want to go ahead and address those before I move on. So where did my 2 come from? Right here. So this 2 is coming from the equation for my height. So the equation of my y is 2x plus 1. So once we have this x value, we're plugging that in here to come up with the height of the rectangle, which probably answers the next question also, which is explain how I got the height again. So the height is coming from plugging that generic x value into the function. We've got the sum from 1 to n of 18I over n squared plus 3 over n. And there are a couple of other summation rules that we should know. And one of those is that if I'm adding 2 things, then I can break that apart. And Dr. Diddell made a big point of saying that if you're multiplying things, those do not break apart. Similarly, like if we're taking derivatives and we have addition or subtraction, we can just treat each piece separately. But when you have multiplication, it's more complicated. Same rule goes with summations. So if I have addition or subtraction in between, we can break those into separate parts. So this can become the sum from I equals 1 to n of 18I over n squared plus the sum from I equals 1 to n of 3 over n. I'm going to add to my summation rule box here. Two more rules that come in handy a lot, and that is that if I take the sum from 1 to n of a number, like let's say I was doing the sum of 1 to n of 5, well, if I were actually writing that out, that would say 5 plus 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 5 n times. So the shortcut way of writing that is that this sum will add up to 5n. So whatever the constant is, it's just going to be the constant times n. The other one that we're going to need, or that's helpful, is if I have a constant times some other function. So let's say I have a constant times I, and I'm going from 1 to n. Well, that constant I can actually bring out in front of the sum. And the reason that I can do that is if you think about writing out each of the terms, then you'd be able to factor that constant out of each of the terms. So this is the same as factoring that constant out of the sum. So back up here to our problem. For this first summation, I is the only thing that isn't a constant. And the way that I know that is whatever variable is down here, that's called our indexing variable. So that's the thing that is my variable in the problem, and anything else with respect to the sum is a constant, which means this, I can take the 18 over n squared and pull that out in front of the summation. So that this becomes 18 over n squared times the sum of I from 1 to n. And here, because I again is my variable, that means that the 3 over n is acting like a constant. I want to use the same color. So this whole thing is constant with respect to I. So that means this is just going to follow that summation rule of being the constant times n. So this, we can evaluate that sum by saying that's 3 over n, the constant, times n. On this one, we're going to use our summation rule and replace that sum of I from 1 to n with n times n plus 1 all over 2. So I've got 18 over n squared times n plus 1 all over 2. Plus, here, those n's will cancel out, and I'll get 3. That is almost as simplified as we can make it. I am going to erase this so that I can squeeze into the corner here. Because the one thing that we haven't done along this whole way, and someone has just pointed this out, is do we need to take the limit as n approaches to infinity? And the answer is yes. If we want to take this Riemann sum and turn it into the actual area under the curve, then our actual area, the true area, not an estimate, the true area under the curve is going to be the limit as n approaches infinity, because n was my number of rectangles. So if I shove an infinite number of rectangles in there, then that will exactly give me the area of, and here I'm just going to do 2 quick steps to simplify. So 18 over 2, that's going to simplify to be a 9, and I'm going to cancel out one of those n's. So I'm going to be left with 9 times n plus 1 over n plus 3. So in the limit as n approaches infinity, n plus 1 over n, that limit is going to be 1. Now, Dr. Diddell did say that you are welcome to use your 17A skills and that you don't have to show more work than that. If you want to show more work, one of your options would be to divide every term by n, to break that up into separate fractions. And that's kind of what he did on Wednesday, to treat this as if it says 9n over n plus 9 over n plus 3. And then this n over n will cancel. And in the limit as n approaches infinity, 9 over n was going to go to 0. So this would be 9 plus 0 plus 3, which is 12, which matches what we got before. So we knew that using geometry, we got 12, and now we just did a whole mess of calculus and also got 12.